So, as another talk about energetics, this time 2D to 3D energy transfers or exchanges between two-dimensional and three-dimensional modes in what I want to call thin aspect ratio turbulence. And it's kind of two short segments sandwiched together. The first is work that we did some time ago with Keith Nahn and Peter Bartello. And then I'll show some more recent stuff that I did with Aaron Gertz, who was a master's student of mine recently. So everything that I'm going to be saying, all the simulations that I'll show and whatnot will apply to unstratified fluids. So we've done this all in an unstratified setting, but I'll try to claim at the end. And in fact, Keith, Peter, and myself have written a paper in JAZ recently showing the connection to rotating stratified fluids. And at the end of the day, I'm going to claim that geostrophic to near inertial energy transfers might play a role, a significant role in the energetics of ocean circulation, if you will. Although I won't really get quite that far. Whoops. Okay, so here's an outline. I'm going to start out by just reviewing a hydrostatic instability mechanism. A lot of the work with Keith and Peter was focused on testing the robustness of this mechanism to non-hydrostatic effects. And then the application that I'm going to show is to mid-latitude gyres. Okay, so the instability mechanism, I'm interested in instability of 2D turbulence to small-scale 3D perturbation. So I'm imagining that there's some 2D turbulence that's already there and already sort of mature turbulence, and then I add some 3D perturbations, and I want to see if they grow. And in particular, I'm interested in the thin aspect ratio limit. So thin aspect ratio implies hydrostatic, and if the fluid's also homogeneous or unstratified, that means that the horizontal pressure gradient force is independent of Z. So the pressure term does not appear in the horizontal momentum equation for the perturbations. Capital U is my 2D turbulent flow, and little u is the horizontal part of the 3D perturbation. So if I'm assuming a thin aspect ratio in a homogeneous fluid, I don't have any pressure term in the horizontal perturbation momentum equation. And if little u is small compared to big U, I can write it like this. So my d by dt has advection by the 2D velocity field, and then I have advection of the 2D momentum by the 3D perturbation over here on the right-hand side. Because there's no pressure term, it's decoupled from the vertical momentum equation. So if I ever want W, I can just get it from the incompressibility constraint. So I'm going to just ignore rotation for the moment, and I'll come back and say a little bit about Coriolis effects later. So I got interested in this years ago when Tom Warren, who was at the 96 Newton thing, pointed out to me that my horizontal perturbation momentum equation here looks a lot like the equation for a material line element L, where L is a 2D line element embedded in the 2D turbulence, if you will. So we know that line elements are going to grow. And the only real difference between this equation and this one is that here I'm calling the vector L, and here I'm calling it U, and the sign's different, right? But if you think of the phenomenology of why we anticipate that line elements grow, you might imagine a sort of a random strain argument. So in other words, modeling the terms in grad U as vorticity and strain, and then just thinking of the strain as varying randomly in time. Well, minus a random strain is still a random strain, so the same arguments apply equally in both cases. Actually, this was suggested by Kreiknen some time ago. Okay, so that's the basic argument, and it seems to make sense. Except that I found when I started presenting it that when I threw out the pressure terms, a lot of people would quickly lose interest. And
really scared about the hydrostatic approximation.
Right. So we wanted to so we wanted to test this in a sort of a non-hydrostatic setting where we're keeping all these terms, right? So and at the time, I had some funding to do climate stuff, and I talked with Peter, and we decided this was probably important for climate, and so we were able to get Keith Nahn to come work on it, and use Peter's triply periodic Boussinesq code in a sort of an order 1 aspect ratio cube with no rotation and no stratification to look at this problem. So the first thing we're interested in is, do we see any evidence of this pressureless or hydrostatic growth mechanism, if you will, this advective growth mechanism in a kind of a fully non-hydrostatic context. And then we also had ideas about how the perturbation should saturate, and I thought that the perturbation should grow, but saturate at a level that depends on the aspect ratio. And then even after an initial growth and saturation of the perturbations, I wanted to make the point that that the mechanism was ongoing, and it's just that it went into fueling a cascade of 3D energy rather than a continuing growth of 3D energy. So even after, so in other words, the growth mechanism that causes the initial growth of the 3D energy later, after saturation, leads to 2D to 3D transfer. That sort of acts as a slow damping on the 2D flow. Okay, so what we did then is we had this model in a cube, so cubic, it's 180 cubed, I think, and so pretty low resolution. And we initialized it with 2D turbulence. We kind of let the turbulence run out for a while, so we have just a few eddies in the box that ducting each other around. We start with some initial perturbation, and so the first thing to do is to see if or where the hydrostatic approximation applies. So these are time shots right after we added the 3D perturbation a little bit later, and about 20 or so eddy turnaround times later. The axes are KZ here and KH here. So the blue stuff means the top left part is thin aspect ratio. That's where KZ is big compared to KH. It's where you might expect the hydrostatic approximation to apply. And blue means it's small, so blue means it is hydrostatic. The non-hydrostatic pressure gradient is small compared to my vective terms. Down here it's red. You wouldn't expect it to apply because the spectral aspect ratio is not thin, it's thick. So these are tubes here and pancakes here, if you will. And so initially it seems to make sense, but a little bit later in the integration we're starting to get non-hydrostatic pressure here. This is a viscous effect associated with just the vertical hyperviscosity. But very quickly, more and more the field is red, right? So pressure is non-hydrostatic pressure gradients are in fact bigger than these vective terms, essentially everywhere except maybe right on this axis, right on where the lowest.
Out the sort of vertical mean horizontal pressure gradient from the rest of this.
Yeah, sure. This is the horizontal. Well, I don't have KZ equals 1 on there, so the vertical mean would be KZ. Sorry, KZ equals 0 would be the vertical mean, so I'm just not plotting.
So that's not that.
That's not there. So this is all 3D. Yeah. Okay. So that was. This is just plotting for the same 4 snapshots. An estimate of the growth in the wave. So this is just from taking differences of snapshots of the energy that's in the various Fourier modes. And what you're supposed to see is that the growth here is occurring in this region where it's sort of slowing down here. This is towards the end of the growth phase, but the growth is largely occurring in the region where the hydrostatic approximation did apply, right? So the modes that were sort of more hydrostatic tend to be associated with the initial growth of the perturbation. So the perturbation is growing essentially all along at low horizontal wave numbers and over range of vertical wave numbers, okay? And another way to look at it is just to plot, to bend the growth and some of the pressure term and my advective growth mechanism term bend according to the spectral aspect ratio. So this is just KH over KZ is my epsilon here. That's the horizontal axis going from 0 to 1. And so in other words, 1 means along this line and small means along this line, if you will. And the curves are this is the growth just observed again by differences in snapshots of the energy that happens to be in that wedge of KZ, KH space. This is the growth that I would expect from this advective growth mechanism. And then this is the contribution of the pressure term, right? So this is the contribution of the pressure work term, which you can see is acting to damp the growth. So the non-hydrostatic pressure effects, the non-hydrostatic pressure is much bigger than this term, but it's less aligned with the 3D flow. And it does tend to slow down the growth a bit, but not a huge amount. Even at aspect ratio 1, I'm still getting much more of this growth due to this adductive mechanism than a damping of it due to non-hydrostatic pressure work terms. Okay, this is a plot. Alpha here is a parameter that Keith came up with. And all you need to know about it is that when it's small, it means that the flow is very anisotropic. And when it's 1, or I think 2, actually, the way we defined it, the flow is essentially isotropic. So the 4 panels that I showed earlier are in this initial growth phase here in the first 20 or so eddy turnaround times. We integrated out on the order of 400 or 500 eddy turnaround times. The different curves are different domain aspect ratios, right? Going from thin down here to order 1 up here. And one of the points that I want to make is just that the return to isotropy is relatively slow, right? It takes a long time, even for the cubic box, to return to isotropy from 2D turbulence. It took 200 eddy turnover times for that to happen. Even for an aspect ratio of like 2/3, it's like just barely happening here at the end, right? And a half is here, and so forth. So it looks like for these thinner aspect ratios, it may never, the whole thing may decay before it ever returns to something that's isotropic. So in other words, the saturation level, this is a measure of the RMS value of my perturbation velocity field, seems to scale like the domain aspect ratio up to values of about a half, and then it kind of levels off. Here, and we had an argument as for why that should be the case. Basically, growth of the perturbations correspond to growth of vertical shear in the horizontal velocity, and then you might expect a secondary Rayleigh-like instability, which would mix the momentum and stunt the growth, so to speak. And this is just an attempt to look into that. This is just a measure of the horizontal velocity to the vertical velocity for these different runs. And the point is that at saturation, there's a time scale matching, if you will, between the secondary turnover time scale and the 2D time scale. And it's reasonable. There's a difference of about a factor of 2 over this fairly wide range of aspect ratios. Okay, well, so now I'm looking at transfer spectra averaged over some time period after the perturbations have saturated, right? So the initial growth has occurred, the perturbations have saturated, and the 2D turbulence is slowly spinning down, but basically we can think of it as sort of quasi-stationary for some length of time. What's plotted on the left are the total transfers as a function of horizontal wave number. So they're scaled by kh, so that the area under the curve essentially corresponds to the amount of energy that's being taken out of or put into a given wave number. So negative means that energy is coming out of the low wave numbers, and positive means that it's going into the high wave numbers. So there's a forward energy cascade, right, with energy coming out of the low wave numbers, going through a short inertial range here, and then into low vertical wave numbers. So the left is for the total flow, not making any distinctions between 2D or 3D. The right is the portion of that, well, it is a related quantity. It's just my production term here, this advective mechanism that I was mentioning. So U dot that is what shows up in the energy equation. And we see, so when these curves are negative, it means that energy is coming out of the 2D field, the 2D flow, and into 3D flow. So this is energy being put into 3D modes at low horizontal wave numbers. So the different curves, again, this corresponds to a thin aspect ratio, 0.044, going up to 1/2 would be this one. So the point that I want to make is that this sink of energy coming out of low wave numbers is associated with a transfer of energy from the 2D flow to low horizontal wave number 3D modes, okay? And then the argument is that the low horizontal wave number 3D modes cascade forward and eventually wind up here. Okay, so this is just the curves up here were for aspect ratios ranging from about 0.04 to a half. These are the ones between a half and 1, and we see that we get a nice sort of scale collapse here. So that's just sort of a parenthetical comment. I'm really more interested in the lower aspect ratio runs. So again, we see that there is this forward cascade mechanism. It does seem to be associated with this hydrostatic instability mechanism. And it gets smaller or weaker as the domain aspect ratio gets thinner. And the reason for that is just that the perturbations saturate at a lower level. Okay, so that's essentially the stuff with Peter and Keith. Moving on, I want to put rotation back into it, in fact, a beta plane. And obviously, if we're at small Rossby number, the d by dt term can just be balanced by Coriolis, and you don't necessarily get any growth. You would just get inertial oscillations. However, if we're in a region of the ocean where Rossby numbers are sort of close to 1, if you will, you would expect this mechanism to still give you some growth. So in other words, you have inertial oscillation and a growth term. And then actually embedded in this d by dt term is a stirring mechanism that tends to sort of stir up the 3D perturbations, cascading them to smaller scale. So this would produce the same sort of ribbon-like streaks of divergent flow around eddies that we've seen in a number of talks today. Okay, so what I want to do now is just get rid of pressure, right? I'm just gonna make the hydrostatic approximation, but add some other effects such as Coriolis and beta plane, and consider the ocean mid-latitude double gyre problem. So I'm just going to force a box ocean on a beta plane with a nice sort of canonical forcing that gives me subtropical and subpolar gyres. We expect these sorts of mechanisms to, this sort of energy transfer from 2D to 3D and then a cascade down to dissipation to be relevant only in the measure that the 3D perturbations saturate at a relatively high level. But if I'm going to a thin aspect ratio ocean, presumably they'll saturate at a very low level. So what I'm going to do is cheat. I'm going to force the 3D modes by applying a sort of stochastic forcing at large scales. So just to say it a little bit more cleanly, well, here are my equations. To get rid of the vertically average pressure, I did have to take the curl. Okay, so I wind up with something that looks like the barotropic quasi-geostrophic equation. I have a Rayleigh term here, which you might think of as bottom friction, and a hyperviscous term. Then there's also terms allowing the 3D flow to feed back onto the 2D modes. Okay, so this is going to allow for my 3D flow to act as an effective damping, if you will, of the 2D flow. My 3D equations, I just have to worry about the horizontal momentum equation. I don't have any pressure term. I can get W from the incompressibility constraint anytime it's needed. So I have Coriolis. F depends on Y. I have my production term here. I'm going to apply a sort of a large-scale stochastic forcing. I don't have Rayleigh drag, but I have a biharmonic friction. And then I have terms that, the rest of the advective terms that allow for transfers between various 3D modes, if you will. So those are the equations. The setting is that I'm going to apply a 2D double gyre forcing to the 2D modes or to the vertically average modes. So in other words, I'm forcing with a wind stress or a wind stress curl that just goes like sine of y. So I'm going to get one big gyre in the southern part of the domain and another big gyre in the northern part of the domain. So this is showing a snapshot of the vertical vorticity after the spin up. So I get things like western boundary currents that go out to sea and sort of wiggle around and so forth. My 3D forcing, I'm just going to force the Gravis vertical mode in 3 dimensions. Sorry, I'm just going to force the gravest vertical mode with a stochastic forcing. And it's kind of a large-scale structure to the forcing. I'm forcing mainly in this area here at very large scales, and then just sort of stochastically in time or with an Ornstein-Uhlenbeck process. Most of my runs only have 2 levels in the vertical, so I just have a depth average mode and a 3D mode. But going to slightly higher resolution didn't change the results in any appreciable way. So I want to focus on the transfers. And this is just a plot, again, at steady state showing various terms in the 2D energetic balance. So the black term is forcing. I'm putting the forcing in at large scales. And there's essentially no forcing at small scales. I have transfer terms associated with beta and advection of relative vorticity that essentially take the energy from the basin scales and pile it all up at a sort of a Rhine scale. The Rayleigh term just takes energy away from wherever it is, which is at the Rhine scale. So the Rayleigh energy is a drag term. And then this blue term and yellow term here are sort of new dynamics that relate to interactions with the 3D flow. So the interactions with the 3D flow, in other words, terms that come from here after I would form the energy equation, are putting a bit of energy in. They're actually forcing the 3D flow at very low wave numbers. They're damping it maybe a little bit to the right of the Rhine scale, and then dumping it back into 2D modes at high wave numbers. And that's causing the 2-dimensional hyperviscosity to turn on and dissipate this. Okay, so there's an additional force. The damping basically is mainly the Rayleigh drag, but also this 2D to 3D transfer and forward cascade mechanism, which gets sucked up by the hyperviscosity.
Is that the term R in your equation, or is it an extra term?
The term R is this one.
Okay.
Okay. Yeah.
You have an additional hyperviscosity.
Okay, so I have a hyperviscosity. Yeah, that was A, right? Yeah, okay, yeah. Okay, so look at the blue curve here is the same as the blue curve here. And the other ones are just for cases where I forced the 3D modes a little bit stronger or not quite as strong, right? So this is not the reference simulation, if you will. This is when I forced the 3D modes a little bit harder, and this is when I forced them not quite as hard. These are the 3D spectra, okay, the 3D energy spectra. And then up above are the corresponding 2D spectra. So what we can see is if we force the 3D modes harder, as you'd expect, there's more 3D energy, but less 2D energy, right? So the 2D, the large-scale 2D flow is damped by a presence of more near inertial 3D energy. And that's just because this net 2D to 3D transfer and then forward cascade and increased hyper-viscous dissipation in the 2D equation is enhanced, or is essentially proportional to the level of background near inertial oscillations. Once again, the blue curve here is the same as the blue curve here. So again, it's showing these 2D to 3D transfers as a function of horizontal wave number for this problem. But this time, I'm plotting it for different Rayleigh drags, going from 0 Rayleigh drag to 10 to the minus 7th, which is a kind of number that oceanographers like. So when I had, well, you can see that the Rayleigh drag has almost no effect on the 3D flow, as you'd expect. The Rayleigh drag's in the 2D equation. But it does have a strong effect on the amplitude of this 2D to 3D transfer mechanism, right? So when I have a high Rayleigh drag, basically I have a robust dissipation mechanism in the 2D dynamics, and I don't really get any net damping here, right? I have just as much forcing of the 2D mode, okay, at small scales as I do energy being sucked out of the 2D modes at slightly higher wave number. But as I go down to lower and lower Rayleigh damping, there's less and less of an energy sink associated with the Rayleigh damping. And what happens is this 2D to 3D transfer mechanism kind of comes in and takes up the slack, right? So by the time I'm down to no Rayleigh damping, my 2D to 3D transfer is uniformly negative in this large range of kH. So this is all energy being, it's a damping of the 2D flow, and it's put into, at high wave numbers, it goes back into 3D and gets dissipated. Okay, so as you decrease the Rayleigh drag, as you expect, the solution kind of runs away. It gets more and more energetic. The 2D flow gets more and more energetic as there's less and less Rayleigh drag. But my main point is that this runaway, if you will, is a lot less strong than it would be in the purely 2D case, where I don't have this additional transfer mechanism coming in to provide an additional sink. So I just want to show stream functions for a kind of time average of this spectrum here of this simulation with 0 Rayleigh drag, and a similar run with also with 0 Rayleigh drag, but with no 3D forcing. So on the left, I have no Rayleigh drag and no 3D forcing, so essentially no 3D energy. And on the right, I have Rayleigh drag, but with this 2D to 3D transfer mechanism acting. And so this is in a regime that I like to think of as sort of vaguely oceanographic. I mean, you can still see gyres that look like the ocean gyres. You get a western boundary current and whatnot. You start to see hints of counter-rotating gyres on the edges. In the case with no 2D forcing, in the case where I don't have these 3D modes, this transfer mechanism, I essentially get a very pronounced four-gyre structure. So what's going on here is that the energetics, the energy equation is being balanced by the solution forming a 4-gyre solution to a 2-gyre forcing. So there's essentially no projection of the forcing on the solution, which is to say that the energy balance is being made in this case by there essentially being no energy source, right? In these problems, you apply the forcing as a wind stress, and you have to calculate the energy source. And if the wind stress is a sign,
It's a resonant inertial mode.
no, this is purely 2D. This is all I'm saying here is that we have the forcing is a single sinusoid, so sine 1, 1.
Resonant off-and-off mode.
Yeah, okay, so it's a resonant, okay, so it looks something like that, right? But it excites itself in a way that there's no forcing, there's no energy forcing, right? And so stop. It says stop, so I'll stop.
Question, could you put up your conclusions so we can look at them during the
I
course?
could put up my conclusions, but they're not there. I uploaded the wrong file or something. So, but yeah.
In the particular equation you put up at the beginning, where you remove the pressure, then the solution is everything sort of just goes in a straight line until it collides. Now, when you solve capital U by t equals 0, so what the pressure does when you put it back in is it stops things colliding. So
Yeah.
most important. So if you have a set up data where things could go in straight lines and not collide, then it wouldn't do very much. And if you set up data where things would collide, it would do a lot.
No, but I mean the setup of the data is just turbulence, right? So I mean I have a complicated bit of data and I can integrate the equations and I don't get sync. Well, I mean I have viscosity, right? So maybe that. But no, what I think this stuff, where I think this stuff applies to the real ocean is at high vertical wave numbers and low horizontal wave numbers correspond to very thin things that essentially don't see the stratification. So that's sort of the inertial limit of the inertial gravity wave dispersion relationship, if you will. And I claim that when the Rossby number is reasonably large, that you can get transfers into these modes. Now, if the only mechanism to excite this near inertial energy is sort of balanced to unbalanced transfers, if you will, you might get saturations at very, very low levels. However, if you also have tides and storms and so forth, putting inertial energy into the system. We know it's there, right? This transfer mechanism is active and it's pumping energy in, it's sort of exciting those modes and putting energy into
I'm
them.
trying to be interpret things slightly differently. I don't know where it's helpful. So now when you go to your from where you've got the 2D background, obviously has a vertically mean pressure gradient, and then you're adding the 3D modes on top. And
Right.
KO and TT analysis of the hydrostatic equations actually formally did this decomposition. They said, 2D is well posed, 2D Euler, which is well posed, this pressure gradient that goes with it doesn't depend on height. The rest of the 3D Berger.
Right.
So with rotation there, instead of going in a straight line, it goes round in circles. So that's your inertial loops you were talking about.
Right.
So you've got your background inertial oscillations.
Yeah.
And then, of course, there are still going to be collisions in your 3D mode. That's going to then effectively force there to be a 3D non-hydrostatic pressure gradient, which can now interact with your 2D. So you can, if you interpret things like that, you might be quite helpful in seeing what's going on.
Okay.
I'm not saying there's anything wrong with what you said, it's just
Yeah.
a different way of looking at it.
Okay, yeah, no, fair enough. Yeah.
So Lenoir's MEDI, was that an?
Well, I don't know. I mean, I asked her. I guess I mean, I think her initial conditions did have a lot of internal waves in them, and I'm just not sure whether her MEDI or the cyclostropically adjusted MEDI was close enough to centrifugal instability so
It is
that you
not.
might get this.
Definitely
So you
not.
said it's not.
Yeah, yeah.
But like one point that I didn't make, but might have made, is that this equation, right, if you take various limits where U2D is, say, plane parallel flow or an axisymmetric vortex or quadratic flow or something like that, and also put it into a different coordinate system that's rotating with the strain axis of the 2D flow, you recover kind of classical instability criteria such as inertial instability, centrifugal instability, hyperbolic instability. Those are all basically just dynamics, right?
Then what you would see is negative PV, which I never saw.
Right. Okay. Well, I don't even have any stratification, so there's not really much PV, right? But my point is that when you add random strain to this, when your eddy's now sort of wiggling around a little bit, even when these kind of seat of the pants, like inertial instability criteria, aren't formally met, you can still get transfer. So I don't know if that's what you're seeing or not.
No, because I was careful to see which part was actually at F and which part was kind of steady.
Yeah.
And it was a ratio at least of 1 to 4, 1 to 5 of the steady part compared to the the inertial part. So.
Okay.
Other comments or questions?